We're going to look at the resistivity of conductors, and there's a word that we use, M-A-L-T, MALT. MALT helps us to remember the four factors that affect resistance, and we're going to look at these one by one. The first one is starting with M, and that is going to be material. Okay. Along the way, someone's got every material we use as a conductor, and they've got 1 cubic meter of it, and they've measured the resistance of it, and they've come up with a table. The values they got out of there, they called rho, and they gave it this Greek symbol rho and RHO. Okay, and what they came out with is they came out with a number of resistance per meter of material. And a couple of figures we use all the time is we use copper. Copper is a good conductor, and copper has a very low resistance of 1.72 by 10 to the negative 8 ohms per meter. And the other one we'll look at is aluminium. Aluminium has a resistance of 2.83 by 10 to the negative 8 ohms per meter. So that's their rho factor. We'll look at the next letter now, the A. The A is for the area of the conductor, and they're talking about the CSA, which is the cross-sectional area. So when we look at the end of a wire, here's our wire here, we're really interested in that area of the conductor there, and that will be given to us as millimeters squared when we buy the cable, but unfortunately meters squared is what we need to know, and we'll look at doing some conversions later for that. So when we're talking about the CSA, we're talking about the millimeters squared, which is the cross-sectional area of the cable, and obviously the bigger the cross-sectional area, the less resistance, therefore the more current can go through it, and the smaller the cross-sectional area, the higher resistance and less current, similar to pipes and plumbing. Next one is the L. Here it is here, L, and that stands for the length, and this will be in meters. So how long the cable is. The longer the cable, the more resistance, and the shorter the cable, the less resistance. And longer the cable, we can therefore put less current through, and the shorter the cable, we can put more current through. Last one is T for temperature. Okay, what happens is as a conductor increases, the electrons, the thermal energy, gets the electrons to move faster. As they're moving faster, the drift velocity, the electrical pressure has less effect on them. So as we increase the temperature of a conductor, its resistance drops a little bit, and as we cool it down, the resistance increases. At this stage, we won't be using the temperature in the next lot of calculations, but we will later on. So temperature still plays a factor in our conductors. Hotter it is, the less resistance. So the hotter it is, the resistance increases, so we can put less current through, and the cooler it is, the temperature decreases, making it a better conductor.